the next topic for the higher level syllabus in this is modulus. Now, everybody knows what modulus means. It's also finding the magnitude of something, and it's usually signified by two lines. And this basically means that we find the magnitude of whatever's inside x. That's the real meaning of modulus. But in the case of real numbers, the magnitude just basically means making whatever's inside that positive, because you can't have a magnitude of a negative number. So the magnitude just means making what's inside these two lines for anything that belongs to real numbers, any number that belongs to real numbers. It just means that we make it positive. If I had a function, let's say, I'm going to draw it with red, this function, which was y is equal to f(x), what would the function of modulus f of x be? Y is equal to modulus f of x. So again, what we are doing is we're making whatever's inside this positive. So that means we're making all the outputs positive. And obviously that means that every output must be positive. So if we would want to draw this, we would keep everything in this that's positive. So this would remain as it is, and this would also remain as it is. And then everything that's negative would then be reflected along the x-axis. Only the things that are already negative, that's below the x-axis, would just be reflected along the x-axis, so they come above the x-axis. And that's what y is equal to modulus f of x would look like. So basically, when you do the modulus sign, you keep everything that's positive the same, and then whatever's negative, you reflect it along the x-axis. And now, for the second thing, right, similar function, and we say that this is y is equal to f of x. So now what would be the function of y is equal to f of modulus x? Again, this means that whatever we input, I'm making it positive. Whatever I input, I'm making it positive. So, well, if I input a positive value, I would get the positive value. So everything where x is positive, that's from the origin onwards to the right, would remain the same. So whatever's in green, which is the transform function for f modulus x, would remain the same. But now let's say I input a negative number, and when I input a negative number, I would just get the positive number that's on the x-axis itself. So if I inputted -1, I would not get this value, but in fact I would get the value for +1. And if I inputted -2, I would get the value for +2. So what you do when you want to make this transformation is that you leave everything that's on the right of the origin the same regarding the x-axis, but whatever's on the left of the origin, you just forget about it and then reflect what's on the right of the origin again along the y-axis. And that's what the function for y is equal to f of modulus x is. So again, for y is equal to modulus f of x, you keep whatever's positive for the y on the y-axis the same, and whatever's negative or under the x-axis, you reflect it along the x-axis. And for y is equal to f of modulus x, we keep whatever's on the right of the y-axis the same, the right of the origin with respect to the x-axis, that is, and we forget about what's on the left of the x-axis, and we just reflect what's on the right of the y-axis, and we reflect it onto the left side. Another thing that we would have to do is a reciprocal function. So as the name suggests, we take the reciprocal of whatever function we have. So if I have f of x, then if I have y is equal to f of x, then I'd like g of x to be equal to 1 upon f of x. And given f of x, we would want to know how to draw g of x, or given g of x, f of x, because it's the same transformation both ways. So now let's say I'm given a function. I'm just going to take a polynomial function because that's relatively easier to for the first example. Okay, so let's say this is the function f of x, and g of x is equal to 1 upon f of x, and I want to draw y is equal to g of x. So let's think about what we know about fractions or rational functions as we did last time. Although this does not necessarily need to be a polynomial, so the rational function, everything in the rational functions might not apply, but we just want an approximate of what's happening with regards to this. So first things first, we know that whenever that 0 cannot exist at the denominator. So everywhere where 0 exists, there would be an asymptote. And as the denominator approaches 0, the function gets very large, because I have explained it in my previous video. F of x is equal to 0 wherever it intersects the x-axis. So we mark x wherever it intersects the x-axis and make these asymptotic lines. Now, taking the reciprocal of a function will not change the fact that it's negative. So whatever's negative will remain negative, and whatever's positive will remain positive. So let's look at the things in the middle, at the ends of the asymptotes first. So on the left side of the asymptote, this is going to increase forever, and as we go to negative infinity, it will just keep increasing. So as the negative numbers get a lot larger, this comes closer and closer to 0, and as it comes closer and closer, and as this approaches this value, this intersection over here, it should become larger and larger. So since as f of x becomes bigger and bigger negatively, g of x would become smaller and smaller, and so we'd get something like that. And as this got smaller and closer to 0, f of x, the y value, this would get larger and larger negatively, and so you'd get something like that there. And it's the same thing over here, except, so we have this value, let this value be a. So now we know that at this point, the value of g of x should be 1 upon a, because f of x is a at that point. So now let's assuming that at this point we're assuming that a is greater than 1, and so 1 upon a would be smaller, but it really just depends on the question. So this would be 1 upon a, and that would definitely be a point that it intersects with. And now again, this is approaching 0, right? This f of x is approaching 0, so g of x should again be approaching infinity at that time. So from here it should go up constantly as it approaches the asymptote, and it's the same thing over here. As it's approaching 0, this should go up too, and you would get something like that. And it's identical over here. If this is equal to b, then at 1 upon b, again this is approaching 0, so this will go to infinity, that's approaching 0, so that would go to infinity. And now on the right side of the asymptote, we have this approaching 0 again, so this would go up really high, and it would, let's say this is d, so it would intersect with 1 upon d, it would stop at 1 upon d, and then this starts decreasing again, so the function would start increasing for a while, and again this would, again it would intersect a place where it's 1 upon something, and then this increases again, so this would approach 0 again. And so what you have to do is you have to basically examine f of x and just think about what it, although this might seem vague, just think about what g of x would be considering it's 1 upon f of x. But there are things that we can generalize. That is, so a few rules just to keep in mind for this is that x-intercepts become asymptotes, right, as I explained it earlier. Then if the function increases to negative plus or minus infinity, g of x goes to 0. maximum and minimum, the maxima and minima of the function would be the same at the same place, except the value would just be 1 upon that maxima minima. Yeah, and the y-intercept 1 upon the y-intercept again. If f of x is greater than 1, then g of x is lesser than 1, and if and greater than 0, and if it's negative, then it will be the negative version of that, that is between -1 and 0. And if f of x is between 0 and 1, or -1 and 0, then g of x would be greater than 1 or greater than -1. And just keeping these in mind, you'll be able to graph almost any reciprocal function. So the last thing we look at is the symmetry of functions. Yeah, so there are 3 kinds of symmetry: translational, rotational, and reflection. Rotational symmetry would be if I can rotate a function for it to be the same thing, for it to become itself again. For example, y is equal to x cube is rotationally symmetric, because if I turn this by 180 degrees, it would be the same function. And so rotational symmetry is if I turn it by 180 degrees and it's the same function itself, it's rotationally symmetric. So translational symmetry is basically if I can move the graph and it would be the same thing again. So for example, for sine x, if I move the graph by 360 degrees ahead or behind, it would be the same thing, or any multiple of 360 degrees. So that's translational symmetry. And reflectional symmetry is if I reflect it along a certain axis, if it remains the same. So for example, this parabola, if I reflect it along this axis, it's the same function, and so it has reflectional symmetry. But now algebraically we would want to know if certain things are symmetric or not. And so we look at these 2 characteristics, and one would be if it's rotationally symmetric around the origin. To see if it's rotationally symmetric around the origin, we would have to, so it would be something like the x cube function in this case, right? And we would see in that case that f of x, the negative of f of x is equal to f of negative x. So now what does this mean? It basically means that if I reflect it, let's just take the negative on this side. So f of x should be equal to the negative of x. So it basically means so this negative sign means that I reflected along the x-axis, and then this negative sign means I reflected along the y-axis. So it basically means if I reflected by the x and y axis, it would still be the same function. And that is exactly what rotational symmetry is doing. It's moving this by 180 degrees, which is the same as reflecting it along the x and the y axis. So this is known, if a function satisfies this condition, it's known as an odd function. So any function that's rotationally symmetric around the origin is known as an odd function. And an even function is if any function is symmetric around the y-axis. So something like a parabola. So this is symmetric around the y-axis for y is equal to x squared. And in that case, f of x should be equal to negative f of x. Yeah. So for an even function, f of x should be equal to f of negative x. And why is that? Because like I said, an even function is symmetric around y. And what is the transformation for a reflection along the y-axis? That is to make f of x f of minus x. And so if f of x is equal to f of minus x, then that means that the function remains the same around a reflection in the y-axis. And so that's an even function, and this is the defining equation for an odd function.